Hello there and welcome back. In the previous video we introduced linear temporal logic and we gave some intuition behind the logic and properties that we could express. In this video we will more carefully introduce the syntax of linear temporal logic and make its semantics precise. So, as you may remember from the previous lecture, linear temporal logic is an extension of propositional logic that adds 4 new operators: the next operator, until, globally, and eventually. So next is X, until is U, globally is G, and eventually is F. Before we continue, I should remark on the following. If you look at different sources for linear temporal logic, they may use different notations. So in particular, instead of X for next, some sources use a circle for next. Globally is often depicted using a box, and eventually is often depicted using a diamond. And in particular, spin that you're using for assignment 2 is using this alternative notation. So let's formalize the syntax of LTL. A valid LTL formula is a formula in either propositional logic, so either we have an atomic proposition A, we have the negation of an LTL formula, we have the conjunction of 2 LTL formulas, we have the disjunction of 2 LTL formulas. So this is basically just what we already know from propositional logic. And then we have in the next state some LTL formula phi holds, phi1 holds until phi2 holds, for LTL formulas phi1 and phi2. Eventually LTL formula phi holds, or globally LTL formula phi holds. So this is all that you can write down. Now let's take a look at the meaning of each of these operators. So in order to define the semantics of LTL, we first define when a path satisfies an LTL formula. What it means for a cryptic structure to satisfy an LTL formula will be defined in a subsequent video. So for now, we just define, given a path pi, what does it mean? So when does path pi satisfy LTL formula phi? Now if we look at the Boolean connectives, then they really have their usual truth value. So a path pi satisfies atomic proposition A if and only if A is in the labeling function of the first state of that path. So what's important to note here is that the paths that we use are paths in a given cryptic structure. So any path is just a sequence of states, for instance, pi equals S0, S1, S2, S3, and so on. So in this case, if A is in the labeling function of pi 0, then what we really mean is that A is in the labeling function of S0 if the path starts with S0. Now path pi satisfies not phi if and only if path pi does not satisfy formula phi. Pi satisfies phi1 and phi2 if and only if pi satisfies phi1 and pi satisfies phi2. And pi satisfies the disjunction phi1 or phi2 if and only if pi satisfies phi1 or pi satisfies phi2. So this really is just what we are used to from propositional logic. Now let's take a look at the temporal logic operators that we added. But before we do so, we can have a look at an example. So consider the path pi is S0, S1, S4, S5, and S6, which I highlighted in blue in the Kripke structure on the right. Now, if we look at that, then pi from position 2 onwards, so remember that we have positions 0, 1, 2, 3, 4, etc. So pi from position 2 onward is the suffix here that starts at S4. Path pi from position 2 onward satisfies the atomic proposition 2 coins, because state S4 here satisfies 2 coins. Pi from position 1 onwards, so we're now looking from position S1, satisfies not 2 coins, because the labeling is 1 coin. 2 coins is not in the labeling, so path pi from 1 onwards does not satisfy 2 coins, and therefore it satisfies the negation. From position 3 onwards, the path satisfies 2 coins and coffee selected. And well, since from path from position 1 onwards the path satisfies 1 coin, it also satisfies 1 coin or 2 coins here. So that's the way you can reason about the basic Boolean connectives. Now let's take a look at the additional operators that we had. So a given path pi satisfies in the next state phi if and only if the suffix of that path starting at position 1 satisfies formula phi. So basically what we do here is we just drop the first state of path pi and we look at the remainder of the path. That remainder should satisfy phi. So for example, if we take the path indicated in blue in the Kripke structure, the path satisfies in the next state 2 coins. In the next state, not 2 coins. Why? Well, the path starts with S0, S1. So the path satisfies in the next state not 2 coins if the suffix starting at state S1 satisfies not 2 coins, which in this case clearly is the case. We could also say the path from position 2 onwards, so in state S, the suffix starting in S4, satisfies in the next state 2 coins and coffee selected. So S4 satisfies in the next state 2 coins and coffee selected because S5 satisfies 2 coins and coffee selected. So if we continue with other temporal logic operators, until is an important one. A path satisfies the formula phi1 until phi2 if there is some index j such that from that index onwards the path satisfies phi2. So there must be a point on the path where phi2 becomes true. And for all other positions, so for all suffixes that start before j, phi1 must hold. So basically phi2 must hold for some position j, and at all previous positions I, phi1 holds. So let's take a look at an example again. If we take the same path as before, where we start from S0, S1, S4, etc. That path satisfies not 2 coins until 2 coins holds. Well, that is true because in S0 not 2 coins holds, in S1 not 2 coins holds, and then in S4 2 coins holds. So the index j that we have here is 2. Remember, 0, 1, 2, 3. So the index that we have is 2, so that is the j from which point on, or at which point 2 coins holds, and for all previous states not 2 coins holds. Now let's take a look at the third example. Not 2 coins holds until next brewing coffee holds. So if we look at the path, then in S6 brewing coffee holds. So that means in S5 next brewing coffee holds. And in S4 next brewing coffee holds. And as we've seen before, not 2 coins holds in S0 and S1. So this property also holds. Now, in a similar way, we can define the semantics of eventually. So a path satisfies eventually phi if and only if there is some index on that path such that the suffix of pi starting from that index I satisfies formula phi. So if we again look at our example, the path that we have been considering all along satisfies eventually brewing coffee, because there is an index on that path, namely S6 here, so the corresponding index is 0, 1, 2, 3, 4. There is an index where the state, or where the path starting at that state satisfies brewing coffee. And of course you can mix these kinds of properties with other temporal logics. For instance, eventually 2 coins holds until brewing coffee. So this last property holds when we start or when we reach S4. Here 2 coins starts to hold, and it remains true until brewing coffee is true. The last temporal operator that we considered is globally, and pi satisfies globally phi if and only if for all suffixes, so for all indices I, the suffix of the path pi starting at position I satisfies formula phi. So for instance, the path that we have here satisfies globally whenever we have 2 coins, then eventually brewing coffee. So this is a nice coffee machine where we are guaranteed, when we have inserted 2 coins, to eventually get coffee. So intuitively we can summarize the semantics using a couple of paths. So a path satisfies atomic proposition A if the first state on that path satisfies A. It satisfies next A if the second state on that path satisfies A. It satisfies A until B if there is some initial prefix where A holds but B does not. And then at some point B holds. So A and not B holds on all states before B holds. Eventually A holds if there is a prefix where A does not hold, and then eventually A holds. And globally A holds if on all states on the path A is true. And of course you can combine this. You can for instance say that eventually globally phi, so from some point on some property phi holds forever. Or as we've seen in the examples in the previous video, globally eventually phi, which means infinitely often phi. So you have a path on which you have to see phi infinitely often. So even in this infinite suffix, you're going to run into states where phi is satisfied. So this was a formal exposition of the semantics of linear temporal logic. In subsequent videos, we will look at when a LTL formula holds for a cryptostructure structure as opposed to when a property holds on a given path. Thanks for watching. Until the next time.